In our previous video, we saw that we can get the gravitational potential of some arbitrary mass whose geometry and density distribution we know by integrating over its whole volume, this g rho over r. In this video, we'll use this definition of the gravitational field as the negative of the gradient of u to define what actually is the gravity vector, or the gravitational field around this body. So if we know at some point we have u, let's say we've evaluated u for a coordinate system located here, and we want to get what is the gravity field at that same point, so from the origin to that object. So g is equal to the negative of the gradient of the gravitational potential, and we have the gravitational potential here, so we can say that this is equal to, now expanding the gradient, we have d by dx, d by dy, d by dz of u ijk. So if you're not sure where that came from, go back to the video on the vector operator and refresh your understanding of what is the gradient. So now we can evaluate the gravitational field just by evaluating these three derivatives of u. So we can start with d by dx of u. So that's going to be d by dx of the integral of g rho over r dv. Now, if we at this point just leave rho as some arbitrary density distribution, then we can't really go any further without defining what rho is. So we would have to stop here. To get a little bit further and get to some useful result, we'll make an assumption at this point. So we know that g is a constant, it's the universal constant of gravitation, and we'll also assume now that rho is also a constant. So in that case, we can actually bring the g rho outside of the integral. So assuming rho is constant, we can go to this step, g rho. Now we'll bring the derivative inside the integral over the volume of d by dx of 1 over r dv. At this point, it's useful to remember our definition of r relative to the Cartesian coordinates. So we want to evaluate the derivative with respect to x. So first we have to put in what r is as a function of x, y, and z. So thinking back to our definitions of the vector field, we can recall that r, coming from the Euclidean distance formula, is x squared square root of x squared plus y squared plus z squared. So with that definition in place, we can actually work out this integral here. And we can say that it's equal to negative G rho integral over the volume. And now evaluating this integral by making this substitution, we find that it works out to x over x squared, y squared, z squared to the 3 over 2. And that's because when we put in this definition and we take the derivative, applying chain rule, we get that we have 1/2, negative 1/2, because here r is in the denominator, negative 1/2 times this function to the negative 3/2, subtracting 1 from the exponent, and then multiplied by the x derivative of the internal function, which is 2x. So the 2 cancels out with the 1/2. We get the negative sign out front because the exponent is negative when r is in the denominator, and we're left with x in the numerator. So we can recognize now that this down here again is r. So we can simplify this expression and just say that du by dx is negative g rho integral over the volume of x over r cubed dv. So that's du by dx. Similarly, for d by dy and d by dz of u, we have that those are equal to negative g. We're going to have an integral over the volume each of those has a negative g rho out front. And then what goes in the numerator corresponds to the derivative that we're taking. So we're going to have a y here and a z here, but in both cases we'll be left with r cubed in the denominator. And these are both also volume integrals. Okay, so now we have our 3 derivatives, du by dx, du by dy, and du by dz. So finally, we can evaluate the g field by just substituting these 3 expressions. So this one also had a negative sign out front, so that's going to cancel with all of these negative signs. So we'll be left with, in the case that rho is constant, the gravity field due to some arbitrarily shaped mass is g rho integral over the volume of, in the numerator we're going to have x, y, and z. In the denominator we're going to have r cubed. And these are 3 vector components of the gravity field, I, j, k, dv. So the gravity field due to that arbitrary mass, assuming that it has constant density, is this integral here, which has 3 vector components. And notice there's a positive sign now, and its components are just x, y, and z. So actually its direction straight out this way, as you would expect. So the direction of the gravity field is towards the mass.